Okay, so we're going to start talking about the action potential now. And we have a picture of the action potential right here. But let's understand how this is measured, okay? So we had a picture of a neuron previously. And let's go back to that picture. So here's our picture of a neuron that we drew previously. Now, all you're doing is when you're measuring the action potential, you're sticking a voltage meter right in the axon membrane. So imagine that I'm sticking my voltage meter right here, okay? And of course it's attached to some device, and it's giving me a readout on the voltage coming through, right? Something like that. So I'm measuring the change in membrane potential on that patch of membrane as an action potential passes through. So keep that in mind. Now, here's the shape of an action potential as it's passing by a patch of membrane on the axon. You have an initial phase right here where you're at resting potential. So you're at minus 70 millivolts. That's the resting state of the cell, the resting membrane potential. And then you have this depolarization phase that occurs. And the membrane starts to become depolarized. And it starts to move toward a positive number. In this case, it's slightly above plus 40 millivolts. So it's getting closer to sodium's equilibrium potential. And then you have it coming back down, going through this repolarization phase. And it starts to move toward potassium's equilibrium potential, which is down here where the membrane becomes hyperpolarized. So here it's about, if we were to actually go ahead and go over here, this is about minus 90. Okay, so this is potassium's equilibrium potential. And then it moves back to the resting state, which is the resting potential of the cell membrane. Now remember what we talked about in the previous video, because if you haven't really grasped the material that we talked about in the previous video, I will go back and watch that video again. But if we remember what we talked about, well, if the membrane is going to become depolarized, that means positive charge is coming in. So during this depolarization phase, if we were to cut right through here into the middle, to the peak, right? During this depolarization phase, the membrane is becoming very permeable to sodium, where at the peak, it is at its maximum permeability to sodium. So here's sodium in green. So if I were to look at it, you can think about it like, okay, the permeability of the membrane is becoming very permeable to sodium right here. And the permeability to sodium starts to go back down like that. So this is permeability to sodium in green. Now, when it goes to the repolarization phase, where this peak, it starts to go down. This is 3, right? Well, the membrane is starting to become permeable to potassium. So it starts to become permeable to potassium, and potassium will be in blue, the permeability to potassium. So the membrane starts to become permeable to potassium. So let's actually do this right there. And it's going to look something like this. It's going to become permeable to potassium, but then it loses that permeability to potassium. So remembering that these voltage-gated channels, these special voltage-gated channels that are only on the axon membranes, they go through 3 states, right? Closed, open, inactive. So in the case of the voltage-gated sodium channels, you can imagine that here it is in the closed state. So actually, let me remove this. Right, there we go. So here it is in the closed state. Up to this point right here. So closed up to here, down over here. And then it's transitioning here, and it's becoming open up to this point. And then it goes to inactive up to here. Inactive. Now, in the case of the potassium channels, well, the potassium channels, they are in the closed state right here. and then they start to transition to the open state. And then over here, it starts to go for a period of time to the inactive state, and then transition again to closed, where it can be opened again later. And the voltage-gated sodium channels at this point, when they're inactive, once the membrane starts to go to resting potential, they start to transition to the closed state, where they can be opened again later. Okay? So you can see that the voltage-gated potassium channels are just slightly behind the voltage-gated sodium channels in their mechanism of going from closed to open to inactive. And that leads to the membrane becoming more permeable to sodium first, right here, and then becoming permeable to potassium right here. Now, the reason why you have this initial up, right, this depolarization phase, is that the voltage-gated sodium channels are starting to open up. They're starting to go from closed to open. And then at the peak, they're all basically open. And then in this downhill part, the voltage-gated sodium channels are starting to transition from open to inactive, which happens randomly. And at this point, the voltage-gated potassium channels are transitioning from closed to open. And at this point right here, basically, the voltage-gated sodium channels, most of them are inactive, and they're not conducting their ion anymore, sodium, and the voltage-gated potassium channels are all going to the open state, but eventually they will also transition to the inactive state, and you're going back to the baseline permeability of the membrane, and that leads to the membrane potential going back to the resting state. So we're bringing a lot of different ideas here together, right? One of them is that the permeability of the membrane keeps increasing for one ion as time goes by. And remember, this y-axis is in time in milliseconds. It's not kind of hidden underneath all these arrows, but if you look at your study guide, you can see the y-axis is time in milliseconds. And as time goes by, more of them start to open up. So the permeability of the membrane to that ion starts to increase. So that depolarization phase, initially, you have very few voltage-gated sodium channels opening up, but the action of a few of them opening up leads to more depolarization, which leads to more voltage-gated sodium channels opening up. So the permeability of the membrane to sodium keeps increasing, and more positive charge starts coming into the cell, changing the potential on the membrane to a positive value. And as they start to go from open to inactive, they don't all go at once. And slowly they start to transition to the inactive state. So that's why you have this repolarization phase, but at the same time, you have the voltage-gated potassium channels. They start to move from 0% open to 100% open over this millisecond time point. And then eventually, both of them are going to be in these states where they don't conduct ions. Right? Sodium initially is in the inactive state in the hyperpolarization phase, and then moves to the closed state. And the potassium channels are going to move to the inactive state where they cannot conduct their ion. Okay, so I'm going to get rid of all of this stuff and go back to the initial plot. Now, there is this little thing here that is saying failed initiation, right, and threshold. That means the membrane potential, in this case, has to reach minus 55, meaning it has to increase from minus 70 to minus 55 for an action potential to actually be initiated. Otherwise, you're going to have failed initiation. And why is that? Well, a voltage-gated sodium channel will cause depolarization. But depolarization is a positive feedback loop on more voltage-gated sodium channels opening. So, if this membrane potential increases enough, what will happen is you have enough positive feedback loop for more voltage-gated sodium channels to open up to get past this threshold and depolarize the membrane more and initiate an action potential. Otherwise, what will happen is you will have this initial depolarization, but it's not enough to lead to more voltage-gated sodium channels to go to the open state. And it will be a failed initiation, and the action potential won't be generated. Now the question might be, how do you get to minus 55? And that is a good question. So let's go back to our picture of the neuron. So we said that an action potential is generated right at the beginning of the axon. And we're going to get to this. But this initial depolarization will happen there, and that is because of something that's happening at the soma and the dendrites. So that initial depolarization event will occur there, and then the action potential will move down the axon. Okay? We will cover what that is soon. So let's read. In the figure above, voltage of a patch of membrane is being monitored. The resting potential is minus 70 millivolts. The minimum threshold change in membrane potential is required for an action potential to be generated. In this case, it's minus 55 millivolts. Once past the threshold voltage, enough voltage-gated sodium channels go from the closed state to the open state for the process to be self-sustaining, aka a positive feedback loop. As the potential on the patch of membrane increases, most of the voltage-gated sodium channels are in the open state and potential reaches sodium's equilibrium potential. So reaches, it's never going to really get there, but it's going to get close. It's going to at least try to get to that. This is the depolarization phase 2 in the figure above. As the potential reaches its peak, voltage-gated potassium channels start to go from closed to the open state, and voltage-gated sodium channels are going from the open to an activated state and will remain in that state until the membrane is repolarized. As the ratio of open voltage-gated potassium channels to voltage-gated sodium channels increase, the potential on the patch of membrane starts to drop back towards potassium's equilibrium potential. This is the repolarization phase 3 in the figure above. Note, as we previously calculated, the resting potential for potassium is near minus 90 millivolts. As all voltage-gated sodium channels go to the inactivated state, and a majority of voltage-gated potassium channels are in the open state, the membrane potential reaches potassium's equilibrium potential, which is lower than the resting potential, aka hyperpolarization. This is the hyperpolarization phase 4 in the figure above. The voltage-gated potassium channels then go to the inactivated state, and the membrane potential rises to the resting potential of the membrane. This is phase 5 in the figure above. Once the resting potential is established, both channels start to transition to the closed state. Because of this inactivation mechanism, an action potential can only travel in one direction. This is because the patch of membrane in which the potential change occurred becomes refractory due to the voltage-gated sodium channels being in an inactivated state. The patch of membrane further upstream and adjacent to this patch will have its potential change enough past threshold to start the same process. So this part right here, this is why an action potential only goes in one direction. And let's go back to the picture above before we continue. So we said before that the voltage-gated sodium channels, they're going to be right here to here. They're going to be in the closed state, right? And then basically from here and right here, at least some of them are in the open state. Now, of course, in the middle right here, this is the maximum number of them being open. And the amount of open channels starts to decrease as you get to this side right here, right? It increases on the left side of this open part. It's the number of them opening increases and it reaches that peak and they start to go from open to the inactive state. So we know that in this area right here, they're all inactive. So at this point, even if the potential on the membrane increases, that patch cannot be depolarized because the voltage-gated sodium channels are simply not going to go to the open state because they have to transition to the closed state. And somewhere down here, over here, once the membrane potential is set back to the resting potential, they go to the closed state. Now, if the membrane is depolarized, now the voltage-gated sodium channels can go to the open state again, and you can have the recreation of this action potential. So the patch of membrane further upstream and the adjacent to this patch will have its potential change enough past threshold to start the same process. Thus, through the actions of these two channels, a membrane potential near sodium's equilibrium potential travels down the axon until it reaches the axon terminal ends. So this action potential will simply travel until it reaches the axon terminals. So what I have drawn here is the change in membrane potential and the conductance of sodium and potassium. So the conductance of sodium is in green and the conductance of potassium is in blue. And the y-axis on the left is just the voltage on the membrane. The y-axis to the right is the current across the membrane. Okay, so current is going to be in picoamps. So the action potential is in red. You can see the action potential drawn. You have the initial depolarization phase right here, right? Then you have the repolarization phase, followed by hyperpolarization and back to resting potential. Now you can see that the conductance of sodium across the membrane is increasing. So because conductance is to this y-axis right here, right? So conductance is increasing. It's a positive number because we said if things are moving in, we're going to give it a positive number. If things are moving out, we give it a negative number, right? So conductance of sodium is increasing as more voltage-gated sodium channels start to go from the closed state to the open state, and then it peaks. And at this part right here, as it's going down, right here, you can see that these voltage-gated sodium channels are transitioning from the open to the inactive state until they're right here and they're fully in the inactive state. And then somewhere around here, they're going to start going to the closed state because the membrane has been repolarized back to its resting potential. Now for potassium, because potassium is actually going to leave the cell, so we have a negative amperage. So that's why it's down here. And you can see that, okay, these voltage-gated potassium channels are in the closed state right here, and then they start opening up, and you get more conductance of potassium as potassium leaves the cell. And then it peaks down here, and you get hyperpolarization, but then they start to transition to the inactive state until you reach here. And then once the membrane is repolarized, again, they start to transition from the inactive state somewhere down here back to the closed state, so they can be reopened again. So the shape of an action potential traveling down an axon is the mirror image of the voltage change on a patch of membrane versus time. So let's actually do this very carefully. Here's our normal plot of time in milliseconds and voltage. And remembering that when we have this sort of plot, what we have is, okay, nothing is happening. Then you have the depolarization phase. Then you have the repolarization phase, hyperpolarization, and back to resting potential, right? But we said that, okay, here's my neuron, and right, and we have the axon going out, and we are simply sticking a voltage meter in here, and we are measuring the change in potential of that patch of membrane. So if I was going to actually have a plot of what this action potential looks like, meaning that I have distance as my y-axis, and again, voltage here, well, okay, what is first coming through? Because the first thing that comes through is, for example, here, right? So we'll say A here, and then let's say this comes through next, B, then C, then D, then F, and then G, okay? So let's draw it out. What do we mean by it being a mirror image? So let me draw the mirror image here. Here's the mirror image. So if I am sticking a voltage meter right here, and I'm measuring as this thing is flowing through in this direction, right? Because that's the direction which it's going. It's going toward the axonic terminals. Well, this is a mirror image, right? So this would be A, this would be B, this would be C, this would be D, this would be F, and this would be G. Right? So I see A coming in first, and that's what I see above here, right? A comes in first, followed by B coming through, and here's B, and then C comes through, and here's C, and then D comes through, here's D, and then F comes through, here's F, and then G comes through, and here's G, right? That's why the action potential actually looks like this as it's going through the membrane of the axon in this direction, being initiated here and moving in this direction toward the axon terminals. Now you can see that the membrane behind is hyperpolarized. So the membrane behind right here is hyperpolarized. So the action potential cannot go backwards because the membrane behind it is hyperpolarized and those voltage-gated sodium channels are in the inactive state, right? Again, going back to that point, the action potential can only move in one direction because it's being initiated right here, and it only will go down this direction because as the action potential moves down the axon towards the axon terminals, the membrane behind it is always hyperpolarized, and those voltage-gated sodium channels in that hyperpolarized membrane are in the inactive state, so they're not going to go to the open state until the membrane here is repolarized back to the resting potential, which it is because the membrane back here is actually repolarized back to the resting potential so that those voltage-gated sodium channels can go to the closed state so they can be reopened again. Now, if we look at it here, it has been depolarized. So another action potential can be generated right there, right? Meaning that if you're trying to figure out how is this thing moving down the membrane, well, the front end of it is depolarizing the membrane, right? Because this is the depolarization phase. The depolarization phase was right here, and now it's right over here. And so these channels, these voltage-gated channels in the front, right here, can go to the open state from closed. So how is this thing going down the membrane is that all the way over here in front of it, you have voltage-gated sodium channels that are in the closed state, ready to be opened again, and they're going to go through the same cycle as before. So this is happening so quickly that it looks like this little action potential thing right here is just moving down the membrane where it can't go backwards because the patch behind it is hyperpolarized and those voltage-gated sodium channels are in the inactive state, but all the voltage-gated sodium channels in front of it are in the closed state, and they will start to go to the open state as this depolarization phase of the action potential starts to be felt by them. So it simply feels like this action potential is simply moving down the axon in this direction toward the axon terminals. It is a bit hard to imagine this. You just have to sort of play with it in your head and think about it for a little while, but then you'll see that yes, this is what's happening. Okay? And let me actually erase this and redraw it. So let me just draw the membrane. So I'm just going to have my Y be the voltage. But here's my membrane, my patch of membrane, right? And this is voltage, and this is distance. But this is really my patch of membrane. Okay? What I'll have is, here's my action potential right here. Right? And a millisecond later, I am going to go ahead and draw it in a different color. And a millisecond later, it'll be here. And it has this appearance of moving down in this direction toward the axon terminals. Alright, so just think about this. This is how it works. There's nothing really much else to it. All it is basically diffusion. But I admit, it isn't easy when you first come across this. But, you're coming across this the first time in this class, and we're taking our time going through it piece by piece, instead of when you go to your professional school and this is taught in a couple of days. The strength of this electrical signal is not measured in the amplitude of each action potential peak, as the peak will always be the same amplitude, but by the frequency of action potentials traveling down the axon. The peak amplitude of an action potential is always near sodium's equilibrium potential. Thus, the peak can only change if the sodium concentration is dramatically changed across the membrane. This dramatic change does not occur under normal circumstances. So what is this saying? So if we go back to our picture above for the action potential, way above here, right? And let's get rid of all this stuff. How strong an action potential is, how strong the signal is, because an action potential is just the signal, is not judged by the amplitude of how high this peak reaches. This peak will always be at the same level. Why? Well, this peak is only dependent on the fact that you have outside sodium concentrations, so sodium, of about 145 millimolarity, and about, let's say, 10 millimolarity in, right? Positive outside, and negative in, and you have a chemical gradient pointing in, right, chemical, and you have a voltage gradient or potential gradient pointing in too. As we said previously, these concentrations of sodium are not going to change. That is maintained by the sodium-potassium pump, and you reach a certain steady state of 145 millimolarity of sodium outside and about 10 millimolarity in, right? We had 5 to 15, I think, in the table that we had in the beginning of this chapter or this section. So when you depolarize the membrane and you go negative out, positive in, right? And you still have sodium's concentration being 145 millimolarity, because that's not going to change, right? This is an important concept to remember. And 10 millimolarity in, concentrations are not changing. The chemical gradient is still the same, right? Chemical being in green, but now the potential gradient is pointing in the opposite direction. So the peak of the action potential signal is dependent on the concentrations of sodium inside and outside, right? Because the equilibrium potential for sodium is dependent on that concentration. Now, if I change the concentrations of sodium, maybe put more sodium outside, put more sodium inside, well, then this concentration gradient, this chemical gradient changes, and so the equilibrium potential also changes. And remembering that when you make a membrane very permeable to a certain ion, the membrane potential starts to move toward that ion's equilibrium potential. And that ion's equilibrium potential is very dependent on the concentrations outside and inside. Again, if you go back to that equation, when you set it up to solve for the equilibrium potential, that equation that you guys learned how to use, that equilibrium potential depends on concentration outside and inside. Those are the two variables that you're putting in. So this peak that we see once the depolarization phase is finished, that peak will not change. Every action potential will have a similar peak. Now, this is a signal. What's the difference between a strong signal and a weak signal? And that's what's being told here. The strength of this electrical signal is not measured in the amplitude of each action potential peak, as the peaks will always be the same, but the frequency of these action potentials traveling down the axon. So if I was going to go back and look at right here, so let's get rid of these things right here. And here's my axon terminal here, and we have the soma on this side, right? Well, if I have action potentials moving down like this, I have one, and I have another one moving down also, and I have another one moving down also, and I have another one moving down also, here, right? And they're all at the same peak. I mean, that's what I'm trying to draw it to be, about the same peak. Well, when I compare it to a second membrane, a second scenario, again, distance, and I have something like this. one action potential, then separated very much by, then you have another one, then separated very much and you have another one. This right here is a stronger signal, and this is weaker. Okay? We'll get into what that means. Okay? So in a fixed period of time, so here's my fixed period of time. I'm going, okay, I'm measuring for 10 milliseconds or for half a second, and this is what I capture. And this is what I capture here. Well, in that half a second, I have 4 action potential peaks above and I have 2 on the bottom. So the signal coming in from neuron 1 right here compared to neuron 2 is stronger because I have double the strength in signal than I do in neuron 2. That's what that means. The higher the frequency of action potential is, the stronger the signal. The lower the frequency of action potential is, the weaker the signal. There is a maximum action potential frequency that each individual neuron can reach. This frequency limit is due to the following 2 reasons. So each neuron is going to be unique. Some neurons are going to be fast firing, meaning that the maximum frequency by which they can fire in action potentials is very high, where some are going to be slower firing, meaning that the maximum action potential frequency they can reach is lower. And here's the reasons. The absolute refractory period, the time required for voltage-gated sodium channels to go from inactive to closed. In fast-firing neurons, this absolute refractory period is very short, whereas in slow-firing neurons, this absolute refractory period is longer. So remembering that our voltage-gated sodium channels go from closed to open to inactive back to closed. What it's saying is that in some neurons, this transition from inactive to closed, when the membrane potential is back to resting potential, is very quick. Therefore, now those voltage-gated sodium channels can go to the open state more quickly. Whereas in some neurons, this transition from inactive to closed is slower, meaning that they stay in that inactive state longer when the membrane is repolarized back to resting potential. And this is the absolute refractory period. Not all neurons have exactly the same voltage-gated sodium channels on them, okay? There's going to be slight differences, and that leads to some neurons being fast-firing and some neurons being slow-firing. The relative refractory rate. This is caused by the length of the hyperpolarization phase. Membrane hyperpolarization can be affected by the length of the time voltage-gated potassium channels remain open before becoming inactivated. So, in this case, we're looking at voltage-gated potassium channels. So, voltage-gated potassium channels. And we said that they have closed, open, inactive. And then they go back to closed. So, what it's saying is that if the membrane is hyperpolarized for a longer period of time, it will take longer for the patch to go back to the resting potential and thus delaying the firing of a new action potential. So this is talking about the kinetics of going from open to inactive. In some cases, what you're going to have are you're going to have voltage-gated potassium channels on some neurons that actually the kinetics of how quickly it goes from open to inactive is slower. So if it's slower, let's go back up top. Right here. That means this hyperpolarization phase will last longer. Okay? So instead of being short, so let's actually draw this out. Right? Let's go back down to our little drawing here. So let me... Actually, we're going to go to a different page and do this. And what we'll do is we'll do the distance one because it shows it a little bit better instead of time, voltage, right? So I have one case where my action potential looks like this. And on a different neuron, my action potential looks like this. So this is a different neuron, right? I'm going to draw it in green, where the hyperpolarization phase is longer. Well, that means that this patch right here is not available to be depolarized for a longer period of time. So that will affect how fast that neuron can fire action potentials. If you have this longer hyperpolarization phase, that means your voltage-gated sodium channels are in the inactive state and they haven't transitioned to the closed state, so you can't make them go back to the open state and depolarize the membrane again. So a longer hyperpolarization phase just means that your voltage-gated sodium channels are in the inactive state and you cannot move them to the closed state so they can be opened again. So some neurons are fast firing, some are slow firing. When receiving a maximum stimulus from the soma, some neurons will fire action potentials at a higher frequency than others. This is due to the diversity in the voltage-gated sodium and potassium channels expressed by different neurons. Again, different neurons will express a different set of voltage-gated sodium and potassium channels, and that leads to some of them being slow firing and some of them being fast firing. Okay guys, we're going to stop here. Remember, if you have questions, please post them in Discord, send me an email. I'd rather you post it in Discord because if you have a question, I know other students might have the same question and I can make another video going over the exact questions that you have. Otherwise, well, there's no otherwise. I know you guys will have questions. So just go ahead and ask them. I will answer your questions and you can bend your mind around this. Other students before you have, and they've done well on this section. Okay, we're going to stop here and continue with the rest of the section next. Thank you.